Today I want to talk about something quite different. Basically, I want to talk about embedding. Embedding means finding maps from words to points in high-dimensional Euclidean space, Rn. I'd like to talk about embedding. I'd like to talk about data visualization using force-directed graphs. So those are two big topics, but they both grow out of what we've been talking about, learning morphology automatically, and how is that? If we look at English, we see that there are lots of stems that belong to the signature null, ed, ing, s. And I said, oh yeah, those are verbs, and it's true. And so we've got stems in there like laugh and jump, which take all four of those suffixes. But there are, at the same time, lots of verbs in English, which linguists call strong verbs, which don't form their past tense by adding ed. So you have words like catch, caught, and teach, taught, and sing, sang, and even put. And so if you're going to analyze English, you want to be able to say that there are some words like caught and taught, and one of the parts of some of the appearances of put and sang, which play the same grammatical role as words like jumped and laughed. But to do that, we have to start looking at parts of the data of English that go beyond just looking at words. We have to look at sentences. So the idea is we have to start looking at what words occur around a word. So we can learn things about words by their distribution. That's the term that linguists use to talk about what words a word appears next to or nearby, to the left, to the right, and so forth. So we're going to be looking at words distributions in order to find out something about words. And this is something that leads us to some very cool images. So before I do anything else, I want to show you some images. And what you're going to see are good examples of what's called force-directed graphs, force-directed visualization of graphs. What you're going to look at, what you're going to see are sets of nodes and edges. The nodes you don't really see because they're just points there, but they represent words. And the lines that you see represent edges between pairs of words. And these edges mark similarities. So each word is connected to a bunch of other words that have similar distributional properties. And, well, I won't say anything more. Let's just take a look at some of these things. It's cool. Let's take a look. Yes, so what are we seeing here? We're seeing this fantastic image. This is English, hard as it may be to believe. We're going to see it 3 times. Basically the same thing with a few random differences. What you're seeing is a net. You're seeing the threads. The threads are connecting dots, which are words. Here's a zoomed up. Okay, so there are dots, which are words, and they're connected by threads. And what I have to tell you about is how we decide which words to connect by threads. And that's what this is really about. Oh, here's another one. Yeah, so we're going to take a look deep inside and see what we see. This is pretty amazing. Oh, let's look at another one before we actually talk about content. This one is very similar, but it's zoomed back. We get a slightly better view of what's going on. Let's see. There we go. Yeah, you can see these. Look at that piece down there in the bottom right corner. It's moving off, and we've got these tendrils coming out. The tendrils will turn out to be the most important things, ultimately. All right, just stop. Okay, I can't help myself. Let's look at another one. We're going to look at a couple of them before we actually talk about the math and the linguistic stuff. Okay, let's take a look at this one here. So this, I think, is almost the first one that I did. There's a smaller number of dots there. I think there's only 1,000. It's a smaller corpus. And you can see there more of those tendrils reaching out. And then I'm going to zoom in on some of the nodes that are in those tendrils. Let's zoom in here. And there we go. And what do we see? Individual letters. These are actually middle initials of people's names. Here we've got my, any, our, an. We've got prenominal determiners. Here we've got nominative pronouns. Here we've got prepositions. Here we've got modal verbs: must, should, can, would, will, may. And then it's negative auxiliaries and positive auxiliaries, verbs that invert in questions. And up here, numbers. Okay, well, so you're beginning to see what is, okay, what's this? These are the bare form of verbs, the null suffix on verbs. Okay, you can see what we're heading for. We're looking for ways. We're looking for ways to determine what the grammatical function is of words. And here, these results are coming from looking at long strings of corpora. Okay, so we're moving on from what we did with morphology, where we just looked at word lists. Now we're looking at corpora. We're looking at sentences and looking at the kinds of neighbors words have. All right, that's what we're here to talk about. Okay, let's take a look at some slides. Here in the first slide, we see a matrix. This is sort of the ground truth. And what we see here is a matrix, what we see here is a matrix P, and its rows are words. We're interested in words. They're the things we're going to analyze. The columns correspond to data that we've discovered, or the measurements or properties more generally. So property 1 up down to property n. So rows, words 1 to v. V is the number of words in the vocabulary. Okay, so we've got this matrix, and here we've got data. Now, looking ahead, the properties that we were interested in today are contexts. Yeah, so in fact, this brings us to why you did the second problem in this course, the context and categories. It's so that you would see what we're doing here today. So the properties are contexts, and we are interested in how often each word appears in a certain context. So this is a very sparse graph, or matrix. It's a matrix in which most of the entries are 0, but it doesn't matter. It's our graph. So it's a sparse graph. Just a moment here. Yeah. Another thing to bear in mind is we care about the transpose of this graph, of this matrix. So what is the transpose? It's the matrix in which our rows are the columns of the previous matrix and the columns are the rows. So basically Aij in the previous matrix will appear as Bji, if this is B. That is to say, the ijth element in the first matrix, which was P, is the jith element in this matrix. Okay, so why do we care about the transpose? So that we can do the following. So that we can multiply the original P by P transpose in that order. So why is that? Because the first thing that we're interested in is how similar are two words. In particular, how similar are they in their distribution? So two different words in that original matrix P are two different rows. So how do we compare different rows? Well, the notion of comparison in this context is pretty straightforward, and it's basically going to be inner product. Basically, we look at each column and we ask how many such columns are non-null, and then let's just, to ask how many are non-null is basically to multiply all the corresponding parts, and if both are non-null, then we'll get a positive value, otherwise we'll get 0. So basically, we sum up the products of all the corresponding pairs. That is the inner product, or the dot product. So what we want is to be able to do this for all the different rows. We want for all pairs of rows to calculate the inner product of those two rows. And what is that from a mathematical point of view, from the point of view of matrices? That is just multiplying P by P transpose. So here, what I've written here, M sub ij is equal to M sub ji. That is to say, this matrix, which is the product of the two, it's the inner product of word I and word j's context information, and I'm just repeating what I said to you a second ago. Bear in mind, we could do the same thing with P transpose times P, but that would give us information about how the different contexts relate to one another, which is extremely interesting also. It's just not what we're doing right now. Okay, so now we've got this matrix M, which is symmetric, therefore square. What can we do with it? What can we learn from it? And there's basically two things we can do. We can look at it as a graph, and the other is we can think about embedding it in some high-dimensional space. And we're going to do both. But the first thing we're going to do involves embedding, not graph. So what is a graph? I'll just remind you, a graph is a set of nodes and edges, and oftentimes we will associate with each edge a number, and if so, we call that number a weight, and then we say we have a weighted graph. Okay. There's a natural way to think about a graph as a matrix, M, let's say, and the way that's most natural is what's called its adjacency matrix. And what that simply means is that each node corresponds to a row and a column. Hold on a second. And M sub ij is 0 if there's no edge from I to j, and having no edge is the same as having an edge with a weight 0 if there are weights. And it's a 1 if there is such an edge, or if it's a weighted graph, then we put the actual weight in this particular matrix, this adjacency matrix. Okay, so for us, the nodes are words, and the edges are the non-zero entries in M. Okay, so that's a graph. That's interesting. We'll use it. And embedding is something different. And embedding is a map from words to a point in Rk. Well, what's K? Well, K is some high-dimensional space, but it's up to us to decide how big K is. We're mostly going to be looking at K equals 10. Nothing stops us from making it 50 or 100 or 1,000. And what we're interested in is finding groups of words or relationships between words. So we're interested in asking ourselves questions about how do we find clusters in either case, either the graphs or embeddings, or other kinds of organizations of the word of these words. So that's our task. Well, big graphs are hard to visualize, and Rk is really hard to visualize too if K is bigger than 3, and for that matter, even if it's bigger than 2, even three-dimensional space is hard to visualize, certainly. It is for me, and it's hard to put it on a computer screen. Not impossible, but hard. So one of the ways that people have come up with it, which is very cool, is to talk about force-directed graph visualization, and there's quite a few programs out there that do this. One of the ones that's well known and that I've used and enjoyed using is called Gephi. It's written by some French computer scientists. It's a Java-based program. Now my results were that visualization of M directly didn't seem to give us anything meaningful, even with normalization. I'll talk just a little bit about normalization later on, but basically what I mean by normalization is taking into account the fact that some words like, well, you know, like the and to and and my, some words have a very high frequency, whereas most words in a corpus have low frequency. Even normalizing is difficult to get a useful visualization of this information that we've got so far. Okay, so what we're going to talk about is embedding, and in particular, what could be called spectral embeddings. Any time in mathematics, if you use the word spectrum or spectral, you typically are referring to a set of eigenvalues. And that's what we're using here, a set of eigenvalues and eigenvectors. And here's the basic idea. We think about each dimension in this Rk that we're mapping to. We think about each dimension separately. Well, that's inherent in assigning a coordinate to any particular word. If it's an RK, then we're going to have to come up with k different coordinates. So we're going to have k different maps, and each map is going to be done more or less independently. All right, so let's just think of a sequence of Fs, capital Fs, let's say. And what else? I'll say, what I'm going to say will be true about each one of them. What our goal is to have an F which maps each of the words to a position on some interval on the real line. And now here's the crucial part. If two words are similar in their distribution, then we want those two words to be close together in the image of F. So F is mapping two words to this interval. If the two words have share a lot of context, we want where those two words to be placed to be close. If they don't share intervals, we don't care whether they're close or far apart. So as I indicated here in the note, what that means is if Wi and Wj are similar, then we want the image of under F of Wi and j. We want the square of the difference to be small. All right, so suppose we come up with an embedding. What do we do with that? Well, what I'm going to do here is look for the k nearest neighbors. I'm going to choose a value of k on the order of 5 or 6. And because the words are now embedded, it's a perfectly reasonable question to ask of any word. What are your 5 closest neighbors, or your 10? Closest is very simply defined because it's already embedded in an k-dimensional space. So each word then has a set of neighbors, and then that gives us a graph. We just create a graph where each word is connected to those nearest words. And that's the graph that you looked at, and we'll look at some more examples. We use force-directed methods to look at it. Okay, so let's talk about these properties that form the columns in the very first matrix we're looking at. These are basically context. And as you can see in the slide here, the way I'm going to notate the different contexts that we're interested in is as follows. So W of -1 means the word immediately to the left of the word that we're interested in at a given moment. And W of 1 means the word to the right. It's a little bit like Python's numbering. W of -2 -1 means the pairs of two words immediately to the left. W of -1 and 1 means the pair of words, one to the left, one to the right. Okay? And so what I used in this case was, I think you'll see it on the next slide. No, you won't see it on the next slide. Was all pairs of contexts which derive from trigrams. So one context was the pair of words to the left, one context was the pair of words to the right, and what turned out to be the most interesting context is the one that you've looked at, which is the pair of words, one to the immediate left, one to the immediate right. So these were all contexts that formed the column of the original matrix. And then what we can do is find which contexts individual words occurred most frequently in. And that's what this next slide shows. So the highest scoring trigram contexts in which the word the occurred are, as you can see, even in blank, like even in the, and part of the, and the way, comma, and in the small, and spirit of the, and of all the. Okay, none of these are surprises. And then we can also ask what words also appear. What are the highest frequency words in these contexts? And you see what the answers are here. Even in the is matched by even in even in his, even in there, even in its, even in an, and even in this. Okay, so these aren't big surprises, but mainly the thing to observe is we didn't have to think of these contexts. We looked at every possible context, and we had our computer do it, and it gave us these results, which look perfectly reasonable. Here's another example, which is totally different from the. Take a word like would, which is a modal auxiliary in English, and these are the contexts that it occurs mostly in: that he would, or would be taken, or maybe I would, or he would get, or would be period, or would be considered, or would be comma, or would be a. And then you can see the other words that occur with the highest frequency in this context. Well, you can see that they're all modal verbs, which is hardly a surprise. Okay, so having done that, we now need to turn to eigenvectors. And we're going to turn to the math of it. So we're going to talk about eigenvectors and why they provide the best way, in a certain sense, to embed words. And that the answer to that, the reason for that, is that, provably, it's a mathematical truth that these eigenvectors provide the way of mapping all the words that maximizes this sort of goodness of fit criterion that we talked about. That is to say that m sub ij times the square of the distance between the image of word I and word j squared. That the thing which we desire is automatically met by the eigenvectors. There's something else in there that needs to be borne in mind, and that is, because they're eigenvectors, they have to be orthogonal. And that's probably not a good thing from a linguistic point of view. I don't think we're going to talk about that as such, and it's an interesting question. Anyway, that's the first thing. So that's how we're going to be using the eigenvectors, but then bear this in mind. This is the part that's a little counterintuitive at first. Each of these v's, because they're vectors in this space that we've already set up, has a coordinate, of course, and the coordinates correspond to words. Remember? That's how we started off making this matrix, for example. We listed our words down the left-hand side, and at some point I muttered something about, well, let's alphabetize them. But by alphabetizing them, it means we're assigning a label. Each word corresponds to a particular number. The 10th, the 20th, the 127th dimension is a particular word. So when we pull out a vector, in the particular an eigenvector, each of that eigenvector's coordinates is a number that can be assigned to that particular word, the word the or back or whatever, okay? So an eigenvector is a sequence of numbers, and each number is labeled by a word. So what we're going to do at this point is then sort the coordinates of the eigenvector. And, that sounds really kind of crazy. Why would you sort the coefficients of it sounds like you're moving one coordinate into the coordinate for another dimension. But no, actually, at this point, we've sort of lost sight of the fact that it's a vector as such. And rather, what we're thinking about is how this eigenvector deals with the closeness of two words. So if two words have similar distributions, their coordinate should be close to one another. That's what we're going to get out of it. So stepping back a bit then, we get an eigenvector, and that gives us a location along an interval for each of the words. And because we've got multiple eigenvectors, from each one of them, we get a coordinate for each one of the words. And hey, what that means simply is at that point, we have a coordinate in this k-dimensional space for every word. The coordinate, just to really dot my I's, the coordinate for any given word, its kth coordinate, is the value in the kth eigenvector corresponding to that word. Okay? Now we're going to take a break for some math. Okay, we're recording. I want to share my iPad. Yes, now it's working fine. All right, let's see if we can do this. So what I want to do now is just some math, but I want to connect it up to the problem we're interested in. Okay, so here's the thing. We've got our words, word 1, word 2, down to word V. we want to associate each word with a position on the real line, let's say. And that is, we want to spread the words, stretch the words out along this spectrum, call it, this interval here. And we'd like to do it in such a way that if you've got two words, WI and WJ, which have similar distributions, then they should be close to one another. Okay, so if we've got these two words, and let's say that the position that WI goes, we call it X sub I. And the position that word J goes, we call that X sub J. Okay, so that means if we want to say we want them close to one another, what that really means in terms of, quantitative statement is we want X sub I minus X sub J squared to be small. And when is it that we want that to be small? We want that to be small when those two words show up in the same environments. Well, we have a better way of saying it than in English. We can say simply, we want X sub I minus X sub J squared times WIJ, where WIJ is W, we call it matrix. I think we called it M. So let's go back and make that M times M sub IJ. If M sub IJ is great, that means that word I and word J share a lot of context. So it's this total here for any pair of words, IJ. If MIJ is large, then we want X sub I minus X sub J squared to be small. If MIJ itself is small, let's say it's 0, then we really don't care whether word I and word J are placed close to one another on this spectrum, on this scale here. All right? So since we want this to be true for all words as a whole, we want this to be true for whole, we can say what we're looking for is to find a minimum for the sum over I and J of, let's write X sub I minus X sub J squared times MIJ. Okay, so that's a way to quantify what we're looking for, where what we're looking for means to use the information that we've got about how similar two words are. And when you think about it, this is a very general procedure. We didn't have to be looking at context words. If there was something else that interested us, we could use the same method. We just use that method in order to find some properties for each word. And now we want to find sets of words that are similar with these properties. Okay, so just bear that in mind. Anyway, this is the point here. We've got this quantity that we wish to minimize. Okay, so now let's think some more about that. So in particular, let's expand that square. So that would be X sub I squared plus X sub J squared minus 2xi xj, and the whole thing multiplied by M sub ij. Okay, so we've got three terms there. So let's erase and see what we can do with what we've got now. And just remember, this is a quantity that we're trying to make sense of, or maybe we've already made sense of it, but given some, data, maybe we could find what these X sub I's and X sub J's are. We want an X value for every word, okay? And the secret word here is eigenvectors, but we're not there yet. All right, so we've got this expression down here. We want to look at it some more. So instead of writing it as a sum over I and J, let's actually split that up a bit and say we've got do that a little bit better. Let's say we've got a double sum. So we've got our first term down here. Let's look at our first term. And it's our first term multiplied by the MIJ. So the X sub I is obviously dependent on I, but not on J. So what that means is we can move the X sub I squared, pull it outside the summation over J, And so inside that, we've just got mij. Okay, you happy with that? So I've distributed the mij over all three terms, but I'm breaking this up into three sums now. And we just did the first sum. And then the second sum will be for the x sub j squared, but I'm going to do the summation in the different order just to take advantage of the dependencies. And so in the second case, it's x sub j squared that gets pulled out, and then we sum over I, all the different i's, for the mij's. Okay. And then finally, well, instead of being a plus, why don't we just write it, just be honest about it and say it's a minus. Then we might as well pull the 2 out front. And so here we've got a sum over I and j, and it doesn't really matter what order we put them in. So we've got x sub I, x sub j, mij. All right. Now what we're going to do is define a new variable. What we're actually aiming for is we're aiming for a diagonal matrix from D11 down to DVV. It's going to be in the same world where the matrices are the size of our vocabulary. So it's a diagonal matrix. All the off-diagonal values are 0. All right. So DII, what is DII going to be defined as? It's going to be defined as the sum over some other variable, j, of all the wij's. Okay. So think of this, if you will, is we pick a word I, and we're going to compute DII for it. And what that is will be the sum of the W values for all of the words that it has any similarities to, which would probably just be a smaller number. It could be a lot, it could be small. In any event, we're summing up all those similarities. And that's what those wij's are. So now we've got those DIIs. And you can see that what's nice is they just simplify our algebra a little bit, because this guy here, the sum over j of mij, is just our DII. So I explained it was a matrix so that I could justify calling it DII instead of just, you'd expect me to call it DI or something. But since we're about to turn this into a matrix, I'll just use the matrix algebra for now. And in the second, it's DJJ, and the I is here. In this case, the I just serves as a kind of a local dummy variable. All right, so we've got this here. So and then we're leaving this thing on the right as it is. So let's just rewrite this. We've got the sum over x sub I squared, d sub I, plus sum over j, x sub j squared, djj, minus 2 times this summing over ij, xi, xj, mij. This hasn't changed. Okay, but what do we have here? Well, whatever we have, we've got 2 of them. They're 2 of it. They're the same thing. We just called the variable I in the first and j in the second, but they're the same expression. So these are, well, if we think about it, yeah, we're going to turn this into a matrix talk in just a moment. But here, in any event, we've got 2 times the sum over I of x sub I squared dii minus 2 times this. And what is this? Summing over ij, x, I. And I'm going to write it slightly differently. I'm going to put the, whoops, that's supposed to be an m. I'm going to put the mij in the middle, and then followed by xj on the right. Why am I doing that? I'm doing that so that this notation here makes you think about this as the product of, you could say 3 matrices, but it's really the product of a transpose vector, a matrix, and a vector. So put it this way, this expression here is, okay, if X is a vector, and it's in a space of dimension V, then we've got X transpose, our matrix M, and X. So that this product here of these three matrices is actually defined by what I've written here. We've done some algebra, and lo and behold, once we've done it, what we actually have is something that can be expressed very naturally as a product of three matrices, where the one on the left and the right are really just vectors. I hope you guys all know enough about multiplying matrices. Maybe I should just write something out. So if you've got a matrix here, M, and you've got a vector here, the way we normally, do things, we say that the matrix on the right, to the right of a matrix, a column vector, and we make a product by taking the product of the top row and that vector, and then the second row and that same vector, and so forth and so on. And that will give us a vector as its output. There's also a very lovely situation where if you've got a vector, which is now in row form, so it's a transpose really of a vector, and it actually doesn't even have to be the same vector. They just have to be in the same space. That is to say, if we had a vector transpose Y and a matrix here in the middle M, and we have a vector X, this expression, I hope you know it, it's the sum over I and J of all of the Y sub i's, M sub I, J, X sub J. Okay, that's what you get. That's really the meaning of multiplying a row and a matrix and a column vector. Okay, so let's go back to where we were, which is here. We now have this matrix version of the second product. And then here on the left, what we've got is something much like it, but really quite simple. It's X transpose times D. This is that wonderful matrix, diagonal matrix D that I made up, times X. So this expression is 2 times that minus 2 times that, which is so cool. So far, we're almost done, well, with the algebra. These two things here are the same. I mean, they're equal. They're just algebraic manipulation. So I will erase this part and take one more step in matrix thinking. Okay, so what can we do here? How can we relate these two? Well, it's really very simple. There's the 2. We can pull that 2 out. And then what have we got? We've got xt times d times x and xt times m times x. So it's really the difference between the two matrices d and m and x, like that. So that is very cool. It's X transpose D minus M times X. Okay, so let's think about this D minus M matrix. D minus M. This has a name. It's called the Laplacian. It has lots of very, very cool properties. For us, conceptually, let's bear in mind that the diagonal elements are the sum of the off-diagonal elements. That's how we defined it. And because I defined, because it's D minus M, so we've set it up so that, in fact, it's of the opposite sign. That if the D is all positive, then the off-diagonals will be all negative. People define the Laplacian either way, with a diagonal positive and the off-diagonal negative, or vice versa. And so here I've defined it as d minus m, and so the off-diagonal elements here are going to be negative. Okay, so we've got our diagonal elements, and the off-diagonal elements are telling us what words are similar to one another, what elements are similar to one another. Okay, so having done that now, we actually have an answer to our question. Well, what was the question, you might say? The question was, how do we find a vector x that minimizes, remember, I defined it before as that sum of our ij, blah, 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 blah. It was that xi minus xj, mij. But what that turned out to be is, hey, what we want to do is find a vector such that if you multiply xt times d minus m times x, this will be a minimum. Well, this notation, this is also, there's another notation that's often used for this. It's the inner product of x and d minus m x. And I told you that d minus m has a name. It's called the Laplacian. And we generally write that with a capital L for Laplacian. So another way of writing this, and the standard way of writing this, is that we're looking for a vector x that will minimize this value here, x, the inner product, well, it's the inner product of x and Lx. And this also has a name. This is called the Rayleigh quotient. If we simply require that the length of x be 1, if we don't put that condition in, then the Rayleigh quotient is defined, ends up being the same thing as, you just normalize by the length of x. Or in this case, really, by the inner product of x and x. Okay, and then it turns out that the vectors that minimize this value are the eigenvectors of the Laplacian. So all we have to do is plug this matrix into what's the package in Python called? Anyway, all we need to do is plug it into our ability to crank out eigenvectors, and we will have these numbers. So the numbers that we need. We will have a way of placing words on a line such that if two words have a similar distribution, they will be close to one another. Okay, let's stop here now for a moment and see where we are and figure out what we're going to do next.